talk about writing differential equation models. In this example, the Calvin cycle uses carbon dioxide to produce glucose. In the process, we consume ATP and NADPH. Write a model of the process using the following assumptions. Drawing a diagram is recommended. So let C be the concentration of carbon dioxide, G be the concentration of glucose, A be the concentration of ATP, and N be the concentration of NADPH. Our variables are C, G, A, and N. So the first thing I'm going to do is I'm going to draw boxes for each of these variables. These are going to help me follow the inflow and outflow from each variable. Our first assumption says carbon dioxide is produced at a constant per capita rate of 5.1 per minute. So the first thing I'm going to do is I'm going to draw an arrow going into the box with C in it, because this represents an inflow into the concentration of carbon dioxide. So we're increasing the amount of carbon dioxide because carbon dioxide is being produced. And this is at a per capita rate. So whenever we say per capita, that means we multiply by our variable. And since our number is 5.1, it's going to be 5.1 times C. Again, it's per capita, which is why we write our variable. Our next assumption says ATP is consumed at a constant rate of 0.5 per minute. We're going to have an arrow going out of A because this is an outflow. This is the rate at which ATP is being decreased. And it's a constant rate, which means it's just 0.5. We're not going to multiply by A, which is our state variable, because it doesn't say per capita. If it did say per capita, then it would be 0.5A. But since it just says that there's a constant rate, we'll just write 0.5. Our next assumption says that when a molecule of carbon dioxide, so this is a molecule, comes into contact with one molecule of ATP, when I read that, the first thing I think about is carbon dioxide times ATP. Because when something comes into contact with another, you're going to multiply it because it's going to be a probability. And we also have one molecule of NADPH that is going to be coming into contact. So we'll multiply by N because it's also a probability of all three of them coming into contact. So essentially, whenever you see the phrase comes into contact or X meets Y, you're going to multiply. The assumption also tells us that when these three come into contact, a molecule of glucose is produced. So immediately I know that there will be an arrow going into G because there's an inflow into the concentration of glucose. Essentially, when these three variables come into contact, the concentration of glucose is going to increase by one molecule. At the same time, carbon dioxide is consumed. So we're going to have an arrow going out of carbon dioxide with those same variables. Because when a molecule of carbon dioxide meets a molecule of ATP, which meets a molecule of NADPH, then because of all those three, one molecule of carbon dioxide is lost. So we have an outflow out of the concentration of carbon dioxide, which means that this is the rate at which the concentration of carbon dioxide is decreasing. And since we've been told to use a proportionality constant of 0.78, we're going to multiply both of these by 0.78. The next assumption tells us that the production of NADPH, so immediately I know that there's an arrow going into N because this is the rate at which NADPH is produced or being increased or being added to. This is proportional to the inverse of the carbon dioxide concentration. So when something is proportional to another thing, that means that you're going to multiply by whatever the other thing is. So here, it's proportional to the inverse of the carbon dioxide concentration. And inverse is the same as saying the reciprocal of. So we're going to do 1 over C. because that is what the reciprocal of the concentration of carbon dioxide is, and that is what we call the inverse. And since it says that this is times the concentration of NADPH, times is another word for multiply. So you multiply by N, and it's with a proportionality constant of 2.01. So we have 2.01 times 1 over C times N. And since those were all our assumptions, we can now write our differential equations. So I'm just going to look at the inflow minus the outflow. For C prime, it's 5.1 C minus 0.78 CAN. G prime is just 0.78 CAN because we only have an arrow going into G, so it's an inflow. A prime, we have an arrow going out, so it's an outflow, which means it's negative 0.5. And for N prime, we have an inflow arrow only, so it's 2.01 times 1 over C times N. And we're not going to subtract by anything because there's no arrow going out. I hope this video helped you better understand how to write differential equation models. I definitely tried to include the various kind of phrases you might come across, such as proportional to, inverse, times, per capita. But if you would like me to do another example, let me know in the comments and I will do that.